Hey, what's going on? Today we are talking about limiting and excess reactants in stoichiometry. So we already saw what stoichiometry is defined as, and it's just a comparison of amounts used versus amounts produced. How much reactant you start with compared to how much product you end with. We know it's based off of a balanced chemical equation, and we know it's going to use a new conversion factor called the mole ratio, and we could use the mole ratio to switch from any substance to any other substance in a chemical reaction as long as we identify the coefficients. Also keep in mind we'll be doing conversions from mass, volume, or representative particles, typically mass, or may convert into mass, volume, or representative particles. And again, typically mass will be the most common example you'll see. So let's pretend we're going out to a picnic and making some hot dogs, and we have the following ingredients. These are our reactants. We have a pack of hot dog buns, which come in a pack of 8. And then we have a pack of hot dog wieners, which come in a pack of 10. So this is a very classic example of a limiting reactant. How many hot dogs can be made? Well, of course, you know the answer is that we can make 8 hot dogs. So we got to ask ourselves, well, what is the limiting factor? In this case, it would be the hot dog buns. Well, what is the excess or remaining ingredient? And that would be the hot dog wieners, leaving us with 2 remaining. So this is essentially all we're looking at when we talk about the limiting reactant, in this case the buns, versus the excess reactant, in this case the wieners. But of course we're going to use a little more math and the balanced equations that we see in stoichiometry. So what is the limiting reactant? It's the reactant that is used up first in a reaction. Because it gets used up first, the reaction stops once this reactant has run out. Therefore, this reactant will determine the amount of product you end with. The excess reactant, or the excess reactants, are any reactants that are left over after the reaction stops due to the limitations set by the limiting reactants quantity. So let's take our formula, our recipe for lead-2 nitrate, and apply a limiting reactant problem to this. Again, we can see the formula here. It says 2 moles of lead 2 oxide plus 4 moles of nitrogen dioxide plus 1 mole of oxygen will produce 2 moles of lead 2 nitrate. Well, let's assume that you have 265 grams of lead oxide and 189 grams of nitrogen dioxide. Now, oxygen, which typically comes from the environment or the air around us, is usually in excess because there's plenty of it around. So it's not going to usually limit the reaction. The question is, which of these 2 reactants, lead-2 oxide or nitrogen dioxide, will be our limiting reactant? Which one will we run out first, therefore determining the amount of product that will be produced? And it's the last question, how much lead nitrate, lead-2 nitrate, can be produced? Well, in order to do this, you're going to see we have 2 given quantities. So this is going to require 2 separate stoichiometric problems. So let's address each separately. Starting with 265 grams of lead-2 oxide. Well, we know we're going to have to use the factor label method to convert. And we know the unit we don't want is grams of lead-2 oxide, so we put that on the bottom. We want to convert grams to moles. This will allow us to get to the mole ratio and switch from lead oxide, lead-2 oxide, to compare it to the amounts of lead-2 nitrate. So we don't want lead-2 oxide moles, so to get rid of that, place that on the bottom. We want to now switch to substance B using the mole ratio and compare it to moles of lead-2 nitrate. Now you're going to see that we've already eliminated grams of lead oxide. We went to moles. That allowed us to use the mole ratio to switch to substance B. So now we're out of substance A and in substance B. Now we want to find out how many grams of product can be produced. So to get rid of moles, we put moles of lead nitrate on the bottom, and we want to convert that to grams of lead nitrate. Now you can see how we got rid of the unit moles, and now we are left in grams. So let's look at the conversion factors. Well, we know for every 1 mole of lead oxide, using the periodic table and adding the mass of lead and oxygen, it has a total molar mass of 223.20 grams. Looking at the balanced equation, we can see that for every 2 moles of lead 2 nitrate, we have 2 moles of lead 2 oxide. And in the last conversion factor, we know for every 1 mole of lead nitrate, using the periodic table, 1 lead, 2 nitrogens, and 6 oxygens give us a total of 331.22 grams per mole as the molar mass for lead 2 nitrate. Now that we have our setup complete, it's simply just multiplying the top numbers, dividing by the bottom. 265 times 1 times 2 times 331.22 divided by 223.20 divided by 2 divided by 1, and you get an answer of 393 grams of lead nitrate. So you can see we just did a simple mass to mass conversion. Use the molar ratio provided by the balanced equation and determine the product that could theoretically be produced given 265 grams of lead oxide. Well, with the other reactant, we were given 189 grams of it, in this case nitrogen dioxide. So let's figure out how much product this amount of reactant can produce. So again, going through the same steps, getting rid of the undesired grams unit and converting it to moles. Now that we're in moles, we could go to the mole ratio and relate substance A, in this case nitrogen dioxide, to substance B, our product, lead 2 nitrate, getting rid of the moles of our substance A. Now that we're in moles of substance B, we want to convert that to grams of substance B. Getting rid of the unit moles leaves us in grams. Now again, looking at the periodic table, the relationship is for every 1 mole of NO2, we have a mass of 46.01 grams. Our mole ratio shows us that for every 2 moles of lead nitrate, we have 4 moles of nitrogen dioxide. And again, using the molar mass we calculated earlier, for every 1 mole of lead 2 nitrate, we have a mass of 331.22 grams. 189 times 1 times 2 times 331.22 divided by 46.01 divided by 4 divided by 1, and this time you get an answer of 680 grams of lead 2 nitrate. So now we've completed these two problems, and this is what we've seen. Starting with 265 grams of PbO, that will produce 393 grams of lead 2 nitrate. However, starting with 189 grams of NO2 would produce 680 grams of lead 2 nitrate. So now we've got to look at these values and analyze them to determine which is the limiting reactant. Just like the hot dogs, we had an option of making 8 hot dogs or 10 hot dogs given each individual reactant. And of course, the smaller number, in this case the 8, was the most we could make given the limitations of the buns. Well, here, giving our ingredients, our reactants, we could see we could either make 393 grams or 680 grams of lead 2 nitrate. Well, if the 265 grams of lead 2 oxide could only produce 393 grams of lead 2 nitrate, then it would stop at that point. No more lead 2 nitrate could be produced because our reactant of lead 2 oxide would have run out at this point. That means there would still be enough nitrogen dioxide to continue producing almost twice the amount had the lead 2 oxide not run out. So given that this was our smaller amount, this is going to be the most we can make. And that's going to make lead 2 oxide our limiting reactant. So this is the basis of limiting an excess reactant and how you could use stoichiometric calculations to determine each. Obviously, there's a lot of variations and different questions we could ask with this. We could go on to ask, well, how much how much nitrogen dioxide would be needed to make this amount of product? How much would remain? Or we could compare to other reactants or other products. We could start you in volume or in representative particles, or ask you to end there. Any variation of this, but of course the process and the methods will be the same. So hope you understand now the difference between limiting and excess reactants, and know how to do these molar conversions while combining it with the newly learned mole ratio. Thanks for watching.